Assalamu alaikum wa rahmatullah, and good afternoon to all of our beloved viewers of the Voice of the Cape's Facebook page as well as the Voice of the Cape's YouTube page. It gives me great honor and pleasure once again to be introducing Brother Imaad Isaacs, who is the head of Futures Academy SA's online high school, and he will be going through the content for the physical sciences paper for the upcoming examinations, the trial examinations that all of our beloved matriculants will be embarking upon in the coming days, inshallah. So, this is the final exam preparation, and this section deals and pertains to mechanics, forces, and Newton's laws. As always, I encourage all of you, our beloved viewers, please, if you have family members or friends who are in matric, as well as all of the matriculants out there, please make sure that you forward and share this link to all of the other matriculants who are doing physical sciences and are trying to prepare for the upcoming examinations. And may Allah Almighty God Almighty grant you all the success as you prepare and embark upon your examination journey for the trial exam period, the mock exams, as you say locally, as well as for the upcoming MSc examinations as well, inshallah. Without further ado, we hand over now to Brother Imaad Isaacs, inshallah, who will be conducting today's session on physical sciences. All yours, Brother Imaad.
Okay, assalamu alaikum. Shukran so much, Brother Amir. So, inshallah, let us begin. And the focus today is physical sciences. Once again, final exam preparation. And as Brother Amir mentioned, we are looking at forces and Newton's laws. Okay, so in essence, with this lesson, we're going to start with the section on forces, and then we will move into Newton's laws. Now, of course, you need to know there's some knowledge that you must have coming from your knowledge with respect to vectors, right? So you know in grade 11, you learned about how to draw vector diagrams, how to draw force diagrams and free body diagrams. You also learned about how to resolve vectors into certain components and that sort of thing. And but to sum it all up, we know that in physics, a vector is represented with an arrow, and the length of that arrow determines the magnitude of that vector. And we also know that the arrow then determines the direction of that vector. Okay. Okay, I just want to see if we have a little clip that gives us an example of vectors over there. And then just to also just check quickly, if Brother Amir, I just wanted to double check if my audio, let me just quickly see if I can share my audio as well. If I reshare the screen, does it offer me an option to share audio? Sorry for this. I just realized that the clip has an audio piece as well. Also share system audio. I've switched that on and I've gone to share there. Okay, great. That is with the audio. Okay, so yes, coming back to this, I think we'll mute the screen audio in a moment. But we had a little nice introduction from Despicable Me on what vectors are. So just to refresh your memory.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah! Check out my new weapon. Piranha gun! Oh, yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Do you want a demonstration? Oh, ow! Gosh, it's so difficult sometimes to get the line back inside.
Okay. Oops. Not interested in the rabbits there. Okay. So that is just a reminder on what vectors are, ladies and gentlemen. So you know a vector as both direction and magnitude, and that's going to become particularly important when we start answering the Newton's laws questions, which we might not get through to today, but it's definitely a follow-up and a continuation of today's session. And the reason I mention that is often in sections like Newton's second law questions, where we're looking at the mechanics questions, students do all the calculations correctly, but when they come to the final part of the answer, they ignore saying it's to the right or to the left, right? And often that mark is assigned for the magnitude and the direction, which then means if you've done a complete calculations question, maybe involving pulleys or a block connected by a string, and you calculate the acceleration, or you calculate some of the forces, and you determine where it's actually going, but you don't say to the right or to the left, then you forfeit that entire mark at the end. And remember, every mark counts, because one mark is 0.67% of the NSC examination in physical sciences. Nevertheless, so let's get into this. We're reminding ourselves that we are now looking at question 2. Question 2 questions involve Newton's second law. Generally, question 2 is approximately 16 marks, could be 17, could even be 18 marks, okay? So that's more than 10% of your examination paper. It's not difficult. It's fairly simple. The methods are fairly simple. And if you spend time with this, do 5, 6, 7 examples, you can get the bulk of the marks from question 2. The other reason we're also focusing on this today is because this is often a section that students don't spend sufficient time on in their matric year. And the reason for that is the entire term 1 is usually spent on this content in grade 11. But grade 11 is so far away and so far behind them that they often forget the work, okay? Hence, we're focusing on it over here. The other reason I'm focusing on it is I didn't pay too much attention to it in school, so this is a good time to revisit it as well. Okay, so let's get into it. Before we actually go into Newton's laws themselves, we're going to talk about the different forces. Forces that you are familiar with is weight. Weight is also known as the force of gravity, or the Earth's gravitational pull. We know the normal force, we know frictional forces. Frictional forces are forces that opposes the motion of an object when it is in contact with the object. And then an applied force being a specific push or pull, and then tension, which is a force. It's an internal force that relates to strings, cables, rods, and so forth. Okay. Then, what is the weight? We know that the weight is actually the gravitational force that the Earth exerts on any object that has a mass. So critical to the definition of weight is actually mass. And you know that the force or the magnitude of the weight can actually be calculated by the formula Fg equals m times little g, where m is the mass of an object and little g is the gravitational acceleration of that object. Okay. And then what is the normal force? The normal force we define as the force or the component of a particular force which a surface exerts on an object with which it is in contact, and it acts perpendicular to that surface. So remember that the normal force is always perpendicular to a surface. Okay, what is the frictional force? The force that opposes the motion of an object and which acts parallel to the surface. So remember, your normal force is always perpendicular. Your frictional force will always be perpendicular to a surface. The static frictional force is the force that opposes the tendency of motion of a stationary object relative to that surface, while the kinetic frictional force is defined as the force that opposes the motion of a moving object relative to a surface. Now, there's 3 important things that you must know about frictional forces. Number 1 is that it is proportional to the normal force. So what this means is it depends on the normal force, and if the normal force is greater, so will that frictional force be. Okay, it is independent of the area of contact, and it is independent of the velocity of motion of that particular object. Okay. Now, you must also be able to solve problems in the NEC examinations using the Fs max is equal to the coefficient of static friction times the normal force. So where this Fs max is actually the maximum static frictional force, and mu s is the coefficient of static friction. Then note the following. If a force F is applied to a body parallel to the surface, it does not, if a force F applied to a body parallel to the surface does not cause an object to move, then F is equal in magnitude to the static frictional force, okay? The static frictional force is a maximum just before the object starts to move across the surface, okay? And if the applied force exceeds Fs max, then we find that there is a resultant net force that causes an object to start accelerating, okay? So we're not going to spend too much time here, but to get the idea here is if I have an object and I apply a force to push that object and that object does not move, then that applied force that I apply onto that object will be equal in its magnitude to the static frictional force at that point. However, just before an object starts to move, the applied force will be equal to the maximum static frictional force at the point just before that object starts to move, okay? And if an object starts to move, then we know that there is a net resultant force because the applied force will be greater than the static frictional force. Okay. You must also be able to solve problems using the kinetic frictional force, right? Where Fk is the kinetic frictional force, mu k is the coefficient of kinetic friction, and N is the normal force. Okay. So in other words, this is why we say that the frictional force is proportional to the normal force. It's because we need the normal force multiplied by some constant in order to get what the frictional force will be. Okay, so now let's go to something very important. In the examinations, you must be able, in the CAPS curriculum, to differentiate between force and free body diagrams. Now, our curriculum in South Africa is fairly clear. A force diagram is looking at the object where we draw the particular forces acting on that object. So you see a picture of the object itself. However, we refer to a free body diagram as a dot or a square without arrows going into that dot, but touching that dot, where we indicate all the forces acting on the object, and we indicate it in such a way that we draw them with arrows pointing away from the dot, okay? So in this case, what do we define a free body diagram as? It is the diagram that shows the relative magnitudes and the directions of forces acting on a body or a particle that has been isolated from its surroundings. So in other words, this comes back to something that we defined in one of our other lessons. What is a system? We consider a system to be an imaginary part of the world that we isolate in order to study it. So when you're drawing a free body diagram, you're going to isolate that particular object. You're going to represent that object using a dot, and then you're going to draw the forces acting on that object. You must also be able to resolve a two-dimensional force. So if we talk about the weight or the gravitational force acting on an object, which is on an inclined plane, we must be able to break it down into its various components. Similarly, if I apply a force, let's say I'm dragging a box and I drag that box at an angle, or the force is applied at an angle, then we know that there are parallel and perpendicular components relative to the surface that we must be able to resolve. And we're going to show you this in a bit. And then lastly, determine the resultant or the net force of two or more forces. So here in grade 11, you've come across being able to draw the resultant force when we are summing up forces. That was something that you covered in the grade 11 year. Okay, so to begin, here we've got two diagrams. On the left-hand side of the screen, we've got what's known as a force diagram. And the reason it's called a force diagram is because I see an object and I've got arrows representing the forces acting on the object. Now, in this particular case, I've got the normal force, and let's just assume that this object is resting on a surface, hence that's why I have the normal force represented by N or Fn. And I've got, because the object has mass, and we are on Earth, it has a gravitational force, or the Earth's gravitational pull applied to it, known as the weight. So then on the right-hand side, I've got a free body diagram. Now, in the examinations, when you draw free body diagrams, there's a few important things. Number one, depending how the examiner is instructed, the marking or set it up in terms of whether things are drawn to scale or not, they may or may not penalize you with regards to the length of the arrows, okay? So remember, usually the length of the arrows determine the magnitude of the force. So if I draw a longer arrow for the normal force, then it would mean that the normal force here is greater than the gravitational force. For example, if I draw a longer arrow with the gravitational force here, then it would mean that the gravitational force is greater in magnitude than the normal force. However, in the particular example we have on screen, the normal force and the gravitational force are equal in magnitude. So listen to the word, it's equal in magnitude. And what is magnitude? It's the amount of that object or that force or the amount of something that is actually there. Now, why do we not say that the normal force and the gravitational force is equal to each other? It's because they are only equal in magnitude. Now, remember from the little video we watched a few moments ago that a vector consists of both magnitude and direction. A vector requires magnitude and direction. So for one vector to be equivalent to another vector, it must have the same magnitude and it must have the same direction. If we look at the arrows for the normal force and the gravitational force over here, the normal force is acting upward, perpendicular to a surface that this block is resting on, and the gravitational force is acting downward towards the center of the earth, downwards, right? And so clearly the normal force and the gravitational force are not equal. However, they are equal in magnitude. In other words, if this was a 10 Newton force, then this would also be 10 Newtons, but with different directions. Okay. So one vector is only equivalent to another vector if and only if they have the same magnitude and the same direction. Okay, so coming back to this free body diagram that we see on the right-hand side over here. Important things to note. Your free body diagram's arrows representing the vectors must touch the dot. So in your examinations, draw your dot sufficiently big enough so that you can touch the arrow onto the dot. And if you had other forces acting in the same direction, you can draw it slightly next to it going up, and you should be able to still touch the dot, right? Because sometimes students make the dot too small and then they can't draw all the forces touching the particular dot for the free body diagram. Now, when working with forces, because forces are vectors, we know that in the physical sciences calculations, we indicate direction using positive and negative signs. Hence, we see over here, the normal force is equal to negative Fg. So if, for example, you start this question and you say that I'm going to take upward as positive, then I'm going to say, okay, Fn is just equal to Fn, which is equal to negative Fg, right? Now, Fg is a downward force, hence it is negative. And since nothing is moving in the system, I could sum up the forces here equal to 0. If this is at rest, I could say Fn plus negative Fg, because Fg is downward, is equal to 0, right? That's one way, or rather, sorry, Fn plus Fg is equal to 0. And then I would take it over and I'd say Fn is equal to minus Fg. And that's how I would get this. Right, so remember the negative sign indicates the direction of the force. Okay, let's move forward. Let's look at example 2. I've got an object moving on a horizontal surface or a horizontal plane. Okay, horizontal surface or horizontal plane. A plane is being, a box is being pushed. It's being pushed to the right along horizontal rough surface. So here's our box. We see the box over there. I want you also to note that perpendicular to the surface, because it's in contact with the surface, there is a normal force, and that's acting upward. And the normal force is equal in magnitude to the gravitational force. So the gravitational force is downward with the same length of the arrow over there, acting from the center of the object. Okay. Now, here is a force indicated moving to the left, and it's labeled as the force of friction. right? So from this situation, if we just told you a box is being pushed to the right along a horizontal rough surface, you must be able to draw this force diagram. You must be able to indicate that there's a normal force acting on the object. That's because it's in contact with a surface. You must be able to indicate that the gravitational force acts on that object because we are on Earth, right? And we also need to indicate that there's friction. Now, how do we know there's friction? The friction comes from the word here. It's on a rough surface, okay? So otherwise, they would have told you it's a frictionless surface. And then on this side, we have the applied force. Now, how do we know the applied force's arrow is longer than this frictional force? Well, it's fairly simple. This is because it's being pushed to the right. We need to indicate actually that it actually moves to the right. But it's being pushed, and for this question, I mean, it's a little bit poorly worded here, but let's assume that it's actually moving to the right as well. So we're pushing it, we are pushing, and we are moving the box to the right, okay, along a horizontal surface. So what, oops, what in the world? Sorry for that, guys. Let's go to the free body diagram. So the free body diagram replaces the little box that we see over here with a dot, okay? It replaces the box with a dot. And here we can see there's the normal force, there's the gravitational force, there's the frictional force, and there's the applied force. Okay. Now, what can we say about each of the forces? Well, I'm assuming that the normal force is equal to minus Fg, right? Because they're not equal. But to make the normal force equal to the gravitational force, I take negative Fg, because negative gives you a positive, which will give you the normal force, right? This simply means that they are acting in opposite directions. And the negative that you indicate over here is also indicating that the magnitude is going to be the same, but the direction of the gravitational force is different. So placing the negative in front of it will give us the direction of the normal force. Okay, that's number one. Number two, and obviously if you calculate the normal force here, its magnitude will be minus m times little g. Now, if we compare the forces also, and we speak of these two are equivalent in magnitude, however, the frictional force compared to the applied force. Remember, when a force is a pull or a push, I've got something opposing the motion acting to the left, and I've got an applied force that is pulling that object towards the right. However, because the object moves towards the right, we can conclude that the applied force is greater than the frictional force. And here we see frictional force is less than applied force, or applied force is greater than the frictional force. Okay. Right, so take a moment to let that sink in. Feel free to ask us any questions if there's any questions at this point. Righto. Okay, now we go to example number 3. Example number 3. So, example number 3, remember the first one was just the free body diagrams. We had something at rest. Example number 2 was we're moving an object to the right. Now, in example number 3, we're going to also be moving an object, but when we do so, we are pulling the object. Like, let's pretend there's a box, and I tie a rope to the box, and I drag the rope over my shoulder. Then I'm going to be applying that force at an angle. That's what we need to note here. We are applying that force at an angle. So if we apply that force at an angle, then the applied force will act at a certain angle to the horizontal. Okay. So let's read the example. An object moving on a horizontal surface or plane with applied force at an angle to the horizontal. So there we go. The box is being pulled. It's being pulled to the right with a force applied at an angle beta along a horizontal rough surface. So let's look at this over here. There's my force diagram. I've got, once again, this is moving across the surface, but I'm applying this force at an angle. My frictional force will still be parallel to the surface, because if you take this back to the definition that we started with, we said the frictional force opposes the motion while it's in contact with the surface and acts parallel to the surface. So if this box is moving to the right, friction must be to the left. If the box is moving to the left, then friction must be to the right. So keep that in mind. And then you can see here that this force over here is parallel to the surface. Now we've got our applied force. We once again have our gravity, and we've got our normal force, and they are again equal in magnitude. And we know this because the box is not moving up, it's not moving down, it's moving across the surface. So in the vertical component, right, or in the vertical plane, we find that the forces acting here cancel each other out. Okay, so the net force in the y direction will be 0. Now the free body diagram that we see over here, remember all your forces must touch. There's my normal, there's my gravity, there's my frictional force. Okay, here's my applied force. Now, if you look at this applied force over here, that's acting at an angle. It's also possible to break down an applied force in terms of components. So let's see. Let's talk about this quickly. Let's just bring up a whiteboard. So let's take that applied force. The applied force is acting on the object. So this is my object over there. I believe that when you press shift, you get awesome vectors. That's my applied force, right? So that's F applied. Now, you know the gravity is acting downward. You know that the normal force is acting in this direction. And you know, sorry, I've got sticky keys enabled. Let me not do that. Let me just make this shorter because the gravity and the normal force, let's assume more or less that's equivalent in magnitude, okay? And then we know this is the frictional force. So I know I drew that again. I'm going to change colors over here. So if I go and I change colors, then this force here from your vector addition rules, you look at this blue vector and you look at the, let's make it green, and you look at this other green vector that you have over here, then you know that this will be Fy applied of the applied force, and this blue one over here will be the horizontal component of the applied force, Fx applied. Now, when you get questions in the examination, you may be asked to draw a force diagram or a free body diagram, and you must indicate all the forces acting on it. Now, what I want you to remember is the following. Fx applied, right, plus Fy of the applied force. This means the vertical component and the horizontal component of those forces is equal to the applied force. Okay? So when the examiner asks you to draw all the forces acting on this object, you must remember that the applied force over here is equal to this force plus this force. So you have one of two options when you answer such a question in the examination. You either draw everything we see in red, or you draw sorry, I was looking for the eraser. Or you draw that, right? So you draw either the components of it, or you draw the actual applied force that you see over here. And remember, if you're drawing it on a free body diagram, you're not going to have that green arrow over there. You're going to have the green arrow over here on the dot itself, right? You're going to have it over there, and it will be drawn like that. So you won't have it on this side, because remember, on a free body diagram, all our forces are going away from the dot. So this green arrow is equivalent to the other green arrow that you see over there. And remember, why are they equivalent? Because one vector is equivalent to any other vector if it has the same magnitude and the same direction. So whether I draw a vector here and I draw it over there, as long as they point in the same direction, have the same magnitude, they're equivalent. Okay, so this here is what you see over here. There is my vertical component. There's my horizontal component of the applied force. This here is the normal force that you see over here. Unfortunately, its label has skyrocketed to that end. And then there's the frictional force, and here is the weight. Okay, remember to label your forces appropriately as well. So if X applied, this will be the Fy of the applied force. This here will be your normal force, your gravitational force, which is weight. And this over here will be your frictional force. Okay, so there we go. There we have it. So let's talk about what we see here. Now, here's something very, very important. This is an example that is teaching us that the normal force is not always equal to the weight. It's not always equal to the weight, right? But the weight is equal to the normal force added to the vertical component of the applied force this here. Why? If we ignore these two forces, the horizontal component, and we isolate and only start looking at the vertical components here, let's also tell you that the object is not moving up and down, right? So when I say the object is not moving up and down, and I know that, remember, the sum of all the forces here will be 0 in the vertical plane, right? So let's indicate this. In our vertical plane, okay, what are the forces that we have there in the y direction? So we've got, let's also choose a reference system. So I'm going to take up as positive and take down as negative, right? So I've got F of y, that's our applied component there. I've also then got our normal force, Fn, right, which is also an upward force, so that's Fn over there. And I've got minus Fg, right? So the sum of these three forces, this one plus this one over here, is equal to 0. Now, what can we say about the gravity, the gravitational force, that Fg? If I take that to the other side, I get Fg is equal to the vertical component of the applied force plus the normal force. So in the previous examples, where we saw no other forces acting in the y direction, it was simple because the normal force was simply equal to the gravitational force. Here we note the gravitational force actually is made up of that vertical component of y plus the normal force. Okay, so keep that in mind. Right, let's go to our next slide quickly. Okay, so let's take 30 to 40 seconds to just give that a quick read. Okay, so welcome back, guys. So yeah, so you've taken 30, 40 seconds to just quickly read that question. Example 4 over here, an object resting on an inclined surface. When an object is resting on a rough inclined surface or an inclined plane, we can see over here the normal force will have the same magnitude, but the opposite direction to the perpendicular component of the weight of the object, gravitational force. So here we can see once again we have a force diagram. Okay, we have a force diagram over there, and the weight acts directly downward from the center, the normal force acts upward, and what's happening over here is we need to determine what the magnitude of the normal force will be. Okay, so with a little bit of trigonometric manipulation, you can show that the angle to the horizontal is equivalent to the angle made between the perpendicular component and the weight itself. There we go. Let's just make that bigger quickly. And so let's say here's our inclined plane, right? There's our object. Oh, my angle is not working so well there. Okay, and so there's also this over here, and there's our angle beta, right? We are also well aware that this acts directly downward. Something is conflicting here. There we go. That acts directly downward. That's the weight, Fg. Okay. And then we know that we have a normal force perpendicular to the surface there. That's a bit longer. It's not. That's Fn. That's our normal force. Right. However, this over here can be broken up into components. And so what are those components? Those components look like this. And they look like this in those directions. Okay. So because once again that object is not jumping up and down on the slope, the magnitude of the normal force Fn will be equal to this part over here, which we'll call Fg, perpendicular to the surface. And this part over here we'll call F little g, parallel to the surface. Now, if you draw that triangle, that looks like this, the blue one that you see over there, right? You'll notice it's a right angle triangle. This angle that's in there is beta, the same one that you see over here. Little trigonometric manipulation will show that that's the same. And also, depending on the calculations that you get, you can always manipulate axes, right? Your axis can look like this, x and y. Your axis could also potentially look like this, x and y, okay? But we won't worry with too much of that right now until we look at some calculations. So let's quickly go to these components, right? If that's angle beta, then this part over here, this side over here, is the opposite length to angle beta. And this side that we have over here is the adjacent side. Now, you know from your trigonometric ratios in maths that this here is F little g, right? So let's construct a ratio for the opposite side. We'll say that that's the hypotenuse F little g that involves the opposite side will be the opposite divided by, hey, what am I doing? Sorry. Sine of this rate of this angle over here, beta, is equal to the opposite, which is this side over here, divided by the hypotenuse, which is F little g, right? But we also know that the opposite side was Fg parallel. So we can say that Fg sine of beta is equal to Fg parallel, and that's because Fg parallel is the opposite side, okay? Then if we do this over here, if we construct another trigonometric ratio, if we involve cos, we know cos of angle beta is equal to the adjacent side, but the adjacent side is actually Fg perpendicular divided by F little g. And we solve for that, we get Fg cos of beta is equal to Fg perpendicular. So parallel to the slope, we got a ratio involving sine, and perpendicular to the slope, we got a ratio involving cos. Okay, so let's go back to the summary over here. The normal force will have the same magnitude, but in opposite direction to the perpendicular component of the weight of the object or the gravitational force. So if you look at the force diagram, we've got weight acting downwards, we got the normal force acting perpendicular to the slope. And then because the object is resting on a rough inclined plane, it's resting, right? That means that there is a frictional force, but it's acting opposite to the direction because the perpendicular component of gravity will be this one going down, right? But there will be a component like this that's acting in this direction. At this point, the static frictional force is equal to that over there, okay? So there's our frictional force, there's our normal force, there's our gravitational force. So if we go further, let's see how we can break this up into components. There's the first component, Fg parallel, and there's the other component, Fg perpendicular. We've also seen that Fg parallel is equal to Fg sine of the angle it makes with the horizontal. And we've seen over here that this is Fg times cos of the angle that it makes with the horizontal. Okay? And of course, we know that Fg from the previous section or the previous examples, Fg itself is equal to the mass times the gravitational acceleration. Okay, we've already shown this, but the weight can be resolved into the parallel and perpendicular components. Weight, or Fg, is mass times gravity. Fg perpendicular is mass times gravity, which is the Fg component times by cos of this angle over here. This Fg perpendicular, this component over here, is mass times gravity times sine of this angle that it makes with the horizontal. And also, Fg parallel is equal to negative F times, negative the opposite direction of the frictional force. So if the object is not moving, we know that Fg parallel is equal in magnitude to the frictional force. And there's a free body diagram: friction, gravity, normal force, and Fg parallel. Another important thing is, this is not, you see the example here does not draw Fg. And the reason it's not drawing F little g is because the components are already present. So if you draw the force, you draw the force in its entirety. If you draw the components, you draw the components. But you don't have the components and the force that make up that force. Okay, hopefully that's clear. And then also these things are at right angles to each other. So please be aware of that, right? Please be aware. Don't draw the normal force like this and the frictional force like that. When it's acting on a surface like that, you won't get the marks. Okay. Okay, let's move forward to example number 5. Now, example number 5 is a little bit more interesting because the object is now sliding down a rough inclined plane. So if it's sliding downwards, friction opposes the motion in the opposite direction of its motion. Hence, if the object, once again, is sliding downwards, then friction would act upwards. Okay? If the object was being pulled or dragged upward, then the friction would act in the direction of downward. In this particular case, the object is sliding down a rough surface, hence the friction is upwards, right? Or up the incline. There's our normal force. This is the perpendicular component of gravity. That's the parallel component of gravity, which is down the slope. And there's our friction up the slope. Now, because the object is moving down the slope, it means there's a greater pull down the slope. Hence, the parallel component of gravity is larger in magnitude than the frictional force. Okay? The perpendicular component of gravity and the normal force are equivalent. Okay? Are equivalent. That's equivalent in magnitude, whereas the parallel component of gravity will be greater than the frictional force, for the simple reason that it's actually sliding down the slope, which means a greater pull down the slope. Okay, let's go to example number 6. Right, example number 6. Instead of moving down the slope, the object's now moving up the slope, but it's pulled. And if it's pulled up the slope on a rough inclined plane, the word rough indicates that it's not frictionless surface, right? It indicates that friction is present. Now, because we're pulling upwards, friction must act downward, right, or down the slope. Then, if you look over here, there's now two forces acting downwards or down the slope, or parallel to the slope, but in a downward direction. And that is the parallel component of gravity and also the frictional force. So you see, friction is down the slope, parallel component of gravity is down the slope. There's my normal force. Here is my perpendicular component of gravitational force. And here is the applied force. Now, if we say the object once again is moving up the slope, and it's moving in such a way that it's moving up the slope and it's moving in such a way that the object's actually moving up the slope, it means once again that there's a greater pull up the slope. So we can say that the force that is applied here will be greater than all the sum of the forces acting down the slope. So here, the applied force is larger than the frictional and the parallel component of gravity combined. Okay? Now let's just say this isn't in all cases. This is in the case where there is a net force, meaning the pull that is exerted up the slope is greater than the sum of the parallel component of gravity with the friction. If there's a net force on the surface up the slope, it will cause the object to accelerate. And we know that's coming from Newton's second law. However, if this force here is equal to the sum of these two forces in their magnitude, then the object can still move. But when it's moving, it would then move at a constant velocity. So we would then say in that case, if it's moving up the slope without any acceleration and it's moving at a constant speed or a constant velocity, then the applied force here will be equal to the sum of the gravitational parallel component as well as the frictional force. Okay. Now let's go to a few worked examples. Right, so we may need to stretch there a little bit and get into the work. I'm going to bring up our little whiteboard over there. I'm going to see what was given. Make some space here in the corner. And yeah. Okay, so I'm going to do that calculation there in the corner for worked example number 1. Okay. Let's see. What does worked example number 1 want? A 6 kilogram box is pulled to the right on a horizontal surface. To the right on a horizontal surface by a force of 20 newtons. So we can see that there is an applied force of 20 newtons. It also states that the box experiences a constant frictional force of 3 newtons during its motion. Now, question 1 says draw the free body diagram. Okay, draw the free body diagram. Draw the force diagram. Okay, so in the case of a force diagram, let's see what this is going to look like. Draw box. Okay, that's my attempt at a box. Let's just see something quickly. No. No. Anyway, let's just go with our box, because I think there's some key you press where if you draw shapes with that key, it perfects the shape. But anyway, I don't remember what key that is. Nevertheless, draw the force diagram. So the force is acting on the object. If we draw the force diagram here, first thing we need to note is I will have a force here. This force will be my applied force. Okay, that's the 20 newtons applied force. Then, because it's on a surface, perpendicular to the surface, I'll have another force. And that force that will act like this will be the normal force, Fn, right? Let's make it in Otherwise, it looks like W. Then let's get a purple thing in there. Acting downward, we will have another force. That force will be F little g. That's the force of gravity. And then because there is motion, and they did say the box experiences a constant frictional force of 3 newtons during its motion. Now remember, if it moves to the right, then we know that opposite to that, there will be a force that opposes its motion, and that will be the frictional force. Okay. Right. So that's our force diagram. That's the first question here. The second question is calculate the normal force. Now, we use the gravity over here to indicate what the normal force would be, okay? And we know this because for the magnitude, for number 2, the magnitude, right, of Fn, it's equal to F little g, because this magnitude is equal to the magnitude of that. So if I want Fn, the normal force, I know it's going to equal the gravitational force, but you know, let's say Fg. Let's just say Fg is equal to m little g, and the mass of this object we can see is 6 kilograms multiplied by 9.8. That's going to be 60 minus 1.2 is 58.8, right? 58.8 newtons, right? But we're not done, because they said calculate the normal force acting on the object. So what we did is we calculated the gravitational force. Calculated the gravitational force. So let me just label this as 1, label this as 2. We calculated the gravitational force. However, the gravitational force is equal in magnitude to the normal force. So therefore, we can say the normal force over here is going to equal to 58.8 newtons. Now, once again, coming back to the fact that force is a vector, it requires magnitude and direction. We've only dealt with the magnitude at this point. We must include the direction. And the direction here is 58.8 newtons. That's the magnitude upwards. Now, if this was an exam question and it was worth 2 marks, for example, or 3 marks, you know, formula, maybe because it's a very simple one, formula and actual solution. Let's say the 2nd mark was awarded for this entire thing. If you leave out the word upwards, you would have forfeited the entire 2nd mark. Okay, so be aware of that. Now let's go to question number 3. Question number 3 is asking us to calculate the coefficient of kinetic friction. Now, once again, in physical sciences, you get a mark for the formula if and only if you substitute as well. So let's say the formula for kinetic friction is equal to Fk, or F little k, is equal to mu k multiplied by the normal force. And let's substitute. We know it experiences a constant frictional force of 3 newtons. So the magnitude here is 3. Right? Mu k is the coefficient of kinetic friction, and that's actually what we're solving for, multiplied by the normal force. And we calculated the normal force now. That's 58.8 newtons, and therefore mu k is equal to 3 divided by 58.8, right? 3 over 58.8. And that should give you some solution over there. It's what's that? 0.0 something, a half, 0.05, 0.06. Let's just check. 3 divided by 58.8. Yeah, so that's going to give us 0.0510, so 0.05 to 2 decimal places. Okay. Okay, so for the coefficient of kinetic or static friction, we don't have any units, and so your answer there is 0.05. The next question is calculate the net force. Now, what is the net force? The net force will be the sum of all the forces acting in that plane. So let's go to calculating the net force. F net is equal to the sum of all the forces, but there's only horizontal forces here. So now we say that's going to be let's decide on a reference system, and that's up to you before you even substitute. So we're going to decide to the right as positive and to the left as negative, which then means if I go back to my diagram, the forces acting on this object, the applied forces to the right, and I've decided that I'm going to use that as positive, and this over here is to the left, so I'm going to use that as negative, right? I made that choice. You could decide that to the right is negative and to the left is positive. If the question doesn't stipulate, it is generally easier for you just to go with the direction of motion as positive. Okay, so F net over here will equal that applied force, right, plus F little k, or immediately you could say minus F little k, right? Okay. Or to make it explicit that we're actually dealing with the direction here, F little k, right? That is actually a force in this direction. So the applied force, we know it's 20 newtons plus negative 3, and that leaves us with 17 newtons positive, right? Positive 17, which is therefore F net is equal to 17 newtons to the right. Okay, you must translate the positive answer that you have over here, right, to that being to the right. Okay, right. I think we've got a few minutes for 2 more examples quickly. Let's go to worked example number 2. A 3 kilogram block is pulled to the right by a 15 Newton force applied at an angle of 30 degrees to the horizontal. The surface has a coefficient of kinetic friction of 0.2 newtons. Forgive me, 0.2, right? It's a coefficient of kinetic friction with no units. It doesn't have any units. Okay, so this was made easy for you because they've drawn the diagram, they've indicated the applied force. They didn't draw all the forces, but they gave you an idea of what's actually happening. 3 things we need to do here. Number 1 is we need to draw a free body diagram of the forces acting on the object. Number 2 is we need to calculate the normal force. And number 3, we must calculate the net force. Now, this is that example that we all told you must be very careful about, because we said that the normal force is not always equal in magnitude to the gravitational force. So this is an example where we see that it's not equal to. So let's see what we can do. Draw a free body diagram. So WE2, meaning worked example 2. We draw a free body diagram. We start with this little blue dot. Okay. And let's see. We have our gravity, F little g. We have our normal force acting on the object, Fn, right? We also have, because there's an applied force, so we have this applied force acting at an object. Acting at an angle. What's going on with me today? So this is the applied force, and on opposing its motion, we must have some friction. Okay. Now, although we've drawn this like this, if you use the parallelogram method, you would know that that applied force has components. So if the question says draw a free body diagram, the one option is to draw this for 4 marks, right? The way you see it. The other option, also for 4 marks, would be to draw it with its components. So there's my Fg, there's my Fn, there's my frictional force. Okay. F little f. Now, this force over here has components, right? Remember, if it looks like that, it has a component like that and a component like that. And if you do it in parallelogram method, then you would have drawn it like this with that sort of thing and that sort of thing, right? So that's the vertical component, Fy, of the applied force, and that's Fx of the applied force. So let's draw in those two components. Now remember, it's either this diagram for 4 marks or this diagram you see over here. So there I'm going to put in Fx, and here I'm going to just put it in green. That's the other component, Fy, right? We actually don't know what's bigger, the normal force or Fy or that sort of thing at this point. Maybe we do, but I haven't given it too much thought. Okay, now, here's an example. If this object does not move up or down, right? So remember, this is still worked example 2. This object is not moving on that surface in the vertical plane. It's moving left and right. In fact, in this case, it's moving to the right. So because it's not moving up and down, the sum of Fn and Fy must equal to F little g, okay? The sum of Fn and F little y must equal to F little g. So we've drawn the free body diagram. That's answering the first question over there, question 1. The next question wants us to determine the following. It wants us to calculate the normal force. Number 2, calculate n, or F little n, whatever you want to label it as. So how do we calculate Fn? Well, let's set up an equation. We know that because it's not moving up and down, the sum of these two must equal to this thing. So therefore, F little g, which is the weight, is equal to the sum of the magnitudes of Fn plus Fy. Okay? They want you to calculate this, so that's a simple mathematical manipulation. So Fn is Fg minus Fy is equal to Fn. What was Fg? Fg we can calculate. We know that there is mass times gravity. We know that Fy actually has components. That's going to be minus F sine of the angle we find over there, 30 degrees, okay, is equal to Fn. Now, if you don't know how to get this F sine 30, once again, you can go and you can draw this. There's my 15 Newton, right? This is a component. We know this is 30 degrees over there. We know this component over here. Let's take that component over there. And we know that this is opposite to 30, and we know that this is the adjacent to 30. So for the opposite, we say sine of 30 is equal to the opposite side divided by 15. So 15, which is F applied, sine of 30 will give me that opposite. For the adjacent side here, I will have 15 cos of 30 degrees is giving me the adjacent side. Okay, so if we go to what we see over here, the applied force, which is F, which is 15 newtons, sine of 30 gives me the vertical component. Right, simple trigonometry that you have from grade 10. Okay, so calculate the normal force. It's just now about putting in the actual values, right? I'm going to keep this generic for now until I actually substitute in things. And I'm going to make that, let's just call it angle theta or alpha for now. So this normal force, therefore, the normal force is equal to the mass, which is 3 kilograms, times 9.8 minus 15 times by sine of 30 degrees, okay? And that you can work out, 3 times 9.8, what is 3 times 9.8? 3 times 9.8 is going to be 30 minus 0.6. So 30 minus 0.6 is what? 29.4. 29.4 minus sine of 30 is a half minus 7.5, right? So what does that give you? 29.4 minus 7.5. That should give us 21,9 newtons. Okay. Now, let's ask yourselves or ourselves the question, is 21.9 newtons the answer? Well, no, it's not the answer because force is a vector. And if force is a vector, we must indicate the direction. And since it's the normal force, it's perpendicular to the surface. So you can say upwards, perpendicular to surface, right? That's going all the way straight up. Right, the last question is to calculate the net force. Now the net force, we noticed that there was no vertical displacement, but there is a horizontal displacement. So the net force will be the sum of the forces in the horizontal direction. And there we're looking at Fx and F little f, okay, of kinetic. You could make this little f and subscript k, or F little f k, right, to indicate that it's kinetic frictional force. Okay, so to calculate the net force, let me just make this bigger since we have a lot of the things that we need over here. Okay, so that's question 1. Calculate the normal force, everything we've done on this side here. That's question 2. And now for question 3, where we want to calculate the net force, we can use what we've come across here in terms of the force diagram. So the net force, because this object is only moving or being displaced horizontally, is going to equal the applied force, F little x, the applied force, or that particular component of the applied force, plus F little k, right? F little k. Or F little fk, whatever you've decided to label your frictional force. Now again, before we substitute into this, we need to actually determine a direction, okay? So I'm going to then again take the direction of motion as positive. I'm going to take this direction as negative. In the case of this over here, yeah, we've just looked at the sum, and yeah, so that was fine. So Fx applied, here we can see this is actually the applied portion of Fx, and it's the adjacent, so it will be 15 cos of 30 degrees, so we'll put in 15 cos of 30, right, plus F times, let's make it Fk like that. So I'm going to substitute in here 15 cos of 30 degrees, and then I'm going to say it's plus the negative value of 0,2, 0,2 times by 21.9, because that's the normal force. So the question was scaffolded for you. Okay. We said this will be 7.5. 21.9 divided by 5, or 1/5 of that. 21.9 times by 0.2 multiplied by -1. Sorry, no scientific calculator here. That's 4,38 plus 7.5 gives us 3,12. So the answer here is 3,12 newtons, right? Now, a few things I want you to note just before we continue. This is positive, and because this is positive, the answer is 3,12 newtons to the right. Okay, that's coming from the positive sign over there. Right, we have one more worked example that we'll conclude on. If we take 3.12 newtons, let's just quickly talk about what happened here. This was F k, or F little fk, or sometimes you may just use it as F little k, and that's equal to mu k, the coefficient of kinetic friction, times by the normal force. So the normal force came from the previous question. The kinetic coefficient of kinetic friction came from the given information in the question itself. Okay, let's go to the last works example very quickly. Right. A 20-kilogram wooden box slides up a surface inclined at 20 degrees to the horizontal. The box experiences a constant frictional force of 2.5 newtons as it slides up the surface. So now the box is sliding up the inclined surface. How, what, whatever, right? It's sliding up. The box experiences a constant frictional force as it slides up the surface. So if it's experiencing a constant frictional force whilst it's moving upwards, remember that the frictional force will be acting down the incline. So the first question we have here is draw a free body diagram, and the second question is calculate the net force acting on the object. Okay, so let's make some space quickly. Okay, remember once again the free body diagram is okay. Right, let's wrap up with this question. We're on a roll. Draw a free body diagram. Remember, free body diagrams, we draw it using a dot. So now, there's my dot. Okay, so what are the forces? Well, this is the object. So the one, remember there's a surface. So let's just imagine the surface is there. If we draw the actual box itself, then perpendicular to the surface, that's going to be my normal force, perpendicular to the surface. Then acting directly downwards will be gravity, right? However, gravity has components. Remember that. Gravity has components. So the components of gravity, this is my free body diagram. I have to draw it over here. But what I'm doing on this side is I'm just referencing what I'm going to draw on this diagram. I've got a component of gravity that looks like that. And that is Fg perpendicular. And then I've got another component of gravity like this. That's Fg parallel. Okay. And then in addition to that, I've also got friction acting on that object. And the friction will be a force like this here, F, let's just call it little f, right? And since this object was moving, constant frictional force, it will be kinetic, right? So let's just leave this as capital F, little f. There we go. Okay. And it was sliding upwards. So they don't tell us it has any applied forces, so it's just sliding upwards. So while it's sliding upwards and there's no mention of an applied force, we won't worry with that, right? So when we draw the free body diagram, although you can draw it, one way is to include gravity. The other way is to work with the components of gravity. And I like working with the components because when we solve the questions later on, the components become important. So here's the one force, right? That's Fn. Then the one component of gravity is, I'm going to do it in green, take it straight from here. That's the one component. And again, at a right angle here, that's going to be Fg parallel. Okay, the other component of gravity will be this one. Okay, and that's going to be Fg perpendicular. And then we have the frictional force also over there. Just use purple. We have frictional force. Okay, F, little f. There's our free body diagram represented with a dot. Make sure all your vectors are actually touching that dot over there. Okay, let's see what's next. Calculate the net force. Now, how do we do this? Well, once again, the object's not moving up and down on the slope. It's moving up the slope, down the slope, but it's not hopping in a vertical displacement, like doing this sort of thing, right? So what this means is the net force will only be acting it will be acting in the parallel plane to that slope. So that was question number one. Let me see question number two. Calculate the net force acting on the object. So question number two. So let's just consider the forces here. Well, the net force will be just the forces we see, the purple and this component over there. So F little f is equal to, hi bo, Imaad, what's up with you, dude? F net is equal to F little f plus Fg parallel. Okay. Now, once again, include directions, but in this case, let's just say I'm going to take, just for argument's sake, let's use down the slope down the slope as positive and up the slope as negative, right? Now I'm using down the slope as positive because everything is in one direction, but it doesn't really matter as long as you interpret this at the end. So f little f, that's going to be mu k, right, kinetic friction times the normal force, plus the FG parallel. We've seen this previously. It's m times g times sine of the angle it's making, right? And the angle here is 20 degrees. Okay. Now, mu k times n, that was given. That's actually given, this part here. They told you it's a constant frictional force of 2.5 n. So you don't actually have to work it out. You know that's going to be 2.5. Plus m, the mass of the object is 20 kilograms times 9.8 multiplied by sine of 20 degrees. Okay. And you can verify this. We'll just type this into something. Okay. So anyway, solution is 69,54. 69,54 newtons. Now, once again, we're not done. It happened to work out to be a positive number, and that positive number is very clearly down the slope. So you must write that in, down the slope, because it's a vector, magnitude and direction. So ladies and gentlemen, that brings us to the end of today's session, where we've gone over forces, we've looked at calculating the net forces, setting up equations for the forces. We haven't really looked at acceleration and Newton's second law, but in our next session, we will most definitely look at that in a lot more detail. We now hand back to our brother Amir in the studio. Amir, that's all from me. Shukran.
MashaAllah, we say shukran, jazakallah khair. Thank you very much, and by terima kasih to Brother Imaad Isaacs from Futures Academy, who so beautifully giving over the discourse and preparing all of you, our beloved matriculants, for your physics examinations, inshallah. And I think this is most likely the longest session that we have had, and I hope, inshallah, that everyone has benefited from this. I know physics is said to be the most difficult subject of all. For some people, it's even more difficult than maths, but inshallah, for the preparation from Brother Imaad Isaacs' side, as well as all the sessions where we from VOC, in collaboration with Futures Academy, are trying to aid and assist all of our matriculants to prepare for your examinations. We hope that those examinations will not be difficult at all, and that you will be able to take them head on and be successful in basically completing your matric year. From our side here, we'd like to say once again, shukran, thank you very much to Brother Imaad Isaacs for giving over today's session on physical sciences, and to all of the matriculants out there, and to all of those who tune in regularly to watch these sessions. We thank you very much. We hope that you benefit from these sessions. And of course, as a last reminder, I always remind everyone, please forward and share this link, which is both on the VOC's Facebook page as well as the VOC's YouTube page. Please send this sessions that we are having for the matric revision to all of the matriculants out there who are trying to prepare adequately for the trial examinations as well as the NSC examinations, inshallah. From our side, we wish you all everything of the very best, respected matriculants, for the long week in ahead, inshallah. Please take some time to prepare for your examinations. I hope that everyone has benefited greatly from these sessions. Until we take up the sessions again, we say to all of you, wassalamu alaikum wa rahmatullahi wa barakatuh, and all of the very best, inshallah.